Okay, so we have a ray tracing problem here. We're going to do it graphically, and then we're going to see if our graphing results match up with our calculations. So let's start with graphing first. We have an object located 3 millimeters to the left of a 5 millimeter focal length converging lens. So we've got, let's see what color we're doing. Let's start with blue. So we've got 5 millimeters, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is converging, to remind ourselves. And we have our object is 3 millimeters to the left of a 5 millimeter focal length lens. So let's go 1, 2, 3. And let me erase that. Should be where my object goes. So I'm going to make this 3 tall. So there we go. There's my object. Okay, so the first ray I'm going to do is the ray coming in from infinity. So let's start with red again. Ray coming in from infinity hits my lens and goes through the focal length, the focal point. The next ray is going to be a ray that, let's do the one that goes through the center of the lens. Like that. And actually I wanted to, let me erase that because I really like to do it in different colors because it helps to see what's going on. So let's do this one as a green one. Not perfect, but it'll do. And let's do the last one in yellow. So remember on this one, we did from infinity through the focal point. Now we're going to go through the focal point. So this is going to be kind of tough. I may actually add a line here. Well, I can't do black, but let's imagine let's try blue. I'm going to extend my lens here up. So this is my lens, right? And let's do yellow. So I'm going to go through the focal point, hit the lens, and then out. If I can eyeball this. Through the lens, through the object, through the focal point, and then I'm going to go out like that, parallel to the optical axis. Now the thing to notice is on the right side of the lens, these 3 rays, so this one, and this one, don't converge, right? They don't meet anywhere over here. But if I were to extend them back, let's try that. We'll extend this one back. Just making them dash so that you know they're extended back. And let's go to red and extend this one back. So this is the image space ray. This yellow one was the image space ray back here. This is the image space ray that I'm just going to project back. I'm trying to keep the same slope here, right? And then the green one. So the green one, I'm going to project that back. And I don't have it exactly, right? But you can see they're going to meet somewhere here, somewhere there. So if I pick blue again, and I go to this spot, let's just say it is right around here. Right? This is that's where they meet. So that's pretty interesting that it meets behind the lens, right? And the other thing is, because notice that the dashed lines are virtual, they're not real rays, and neither is my image is a virtual image. So I'm just going to make this a dashed line too, so that we think about it like that it's a virtual image, right? So what happens is when you have rays diverging like this, your eye, just like it did with a mirror, your eye projects back and it sees the image back behind this lens. So let's use our ray tracing information to make some calculations. So first off, let's start with the thin lens equation. And that says 1 over di is equal to is equal to 1 over f minus 1 over d0. And so 1 over di is equal to 1 over 5. No, yep, that's right. Minus 1 over 3. And now I need a common denominator, right? So remember from math when you were in high school, the common denominator would be 15. And in order to have 15 here, I'm going to need to multiply the 5 times 3. So I'm going to have 3 up here. And in order to have 15 over here, I'm going to have to multiply by 5, multiply by 3 here, multiply by 5 here. So I get 1 over di is equal to a negative 2 over 15. And that tells me then that di is equal to negative 7.5 millimeters. Okay, so that was the calculation. Now let's see if that makes sense over here. So if di tells me that I have a negative, so that means a positive is to the right of the lens, a negative value is to the left of the lens. So that's what we're seeing here. And if I count 1, 2, 3, 4, 5, 6, right here I have 6.5. So here from ray tracing, I get di is equal to a negative 6.5. And magnification through calculation, I'm going to have m is equal to a negative di over d0, which is equal to a negative 7.5 over 3, or a negative 2.5. So I have a negative 2.5, which tells me, remember, if my magnification is negative, then, oh, I forgot my negative here, right? So I have a negative here, and then I have a negative here. Two negatives make a positive, so positive 2.5. So that tells me my image should be erect, and it is, right? And it's 2.5 times my object, which it looks like it is here too. And hi is equal to the magnification times h0. And so that's equal to 2.5 times 3, which is equal to 7.5. And let's count that. So 1, 2, 3, 4, 5, 6, 7. It looks like around 7. So hi is equal to around 7 millimeters. My magnification would be, let's say I could just do hi over h0, and that's going to be 7 over 3. So it's very similar, right? I'm not exactly right because I'm not perfectly, I did this all just by hand, but things are matching up. They look pretty close. So that's how you would do that example. I think the interesting thing about this example is that I put my object inside the focal point, right? It's at 3, but my focal point is at 5. And when that happens, I create a virtual image, right, behind the lens. So I have diverging rays leaving the lens, and those rays can be projected back and they look like a real image. So you would see an image looking through the lens from the right side. You'd see an image and it would be erect and it would be magnified compared to my object.